Have you ever really stopped to wonder why a soccer ball eventually stops rolling? Or, on the flip side, how a massive rocket can even get off the ground and blast into space? Well, it all comes down to the same fundamental rules of the game. So, let's dive in and really unpack the physics that basically dictate how everything in our universe moves.
You know, at the very heart of it all, it boils down to these two super simple questions. Think about it. A book sitting on a table just sits there. Why? But if you give it a push, it moves, and then pretty quickly it stops again. Why? The answers might feel like common sense now, but it literally took a genius to figure them out, and his insights completely changed how we see the world.
For thousands of years, the old idea just made sense. You have to keep pushing something to keep it moving, right? You stop pushing a cart, it stops rolling. Seems obvious. But then Isaac Newton came along and totally flipped that on its head. He said no, an object only needs a push to change its motion, to get it started, to stop it, or to make it turn. And that one single shift in thinking, well, it changed everything.
Okay, so to really get Newton's idea, we first have to appreciate a basic fact about the universe. It's kind of stubborn. It has this natural resistance to change. It really prefers for things to just keep on doing whatever they're already doing. And this fundamental property of matter, this stubbornness, it has a name: inertia.
And this is it. This is Newton's first law of motion. What it's really saying is that all objects will fight a change to their state of motion. If it's sitting still, it wants to stay still. If it's moving, it wants to keep moving in a perfectly straight line at a steady speed. It's not going to change what it's doing unless something from the outside forces it to.
So that book on the table, it stays put because of inertia. And, a hockey puck on the ice only stops because of the force of friction. But, and this is the cool part, if you could get rid of friction completely, like on a perfect sheet of air hockey ice, that puck would just keep going and going and going forever. That right there is inertia in action.
All right, so if objects are so stubborn, if they want to just keep doing what they're doing, what makes them change? What gets that book moving in the first place, or what makes that puck eventually slow down? The answer is the absolute key to all of this: force.
A force is really simple. It's a push or a pull. That's it. It's the agent of change, the one thing that can overcome an object's inertia. When a force acts on something, it can cause it to accelerate, which is just a fancy way of saying it can speed it up, slow it down, or change its direction.
But here's the really crucial part. It's super rare for an object to have just one force acting on it. I mean, think about you right now. Gravity is pulling you down, but your chair is pushing you up. An object only actually accelerates if all those pushes and pulls don't cancel each other out. We're looking for the total, the leftover, the net force.
And you feel these forces all the time. Gravity, that's Earth's constant pull on you. The normal force, that's the ground pushing back up on your feet, keeping you from falling through the floor. Tension, that's the pull you feel from a dog's leash. These are the everyday pushes and pulls that, when you add them all up, write the story of how everything moves.
Okay, so we've got inertia, this resistance to change, and we've got net force, the thing that causes the change. But how do they all connect? Well, this is where Newton gave us the golden rule, probably one of the most famous equations in all of physics, and it ties this whole thing together beautifully.
Let's build it piece by piece. First up, you have the cause, the reason for any change in motion. That's our net force, which we'll just call F.
Next, we've got the object's resistance to being changed, its stubbornness, its inertia. We measure this property as mass, and we'll call it m. The more mass something has, the harder it is to get it to accelerate.
And finally, we have the result, the actual effect, the measurable outcome of that force acting on that mass. This result is a change in velocity, which we call acceleration, or A.
And there it is, the elegant connection. The net force equals mass times acceleration. F equals ma. This is Newton's second law. It looks so simple, but it is incredibly powerful. It lets us predict exactly how an object's motion is going to change when we apply a force to it.
And you can feel this intuitively. Just look at this table. Imagine you push two different objects with the exact same amount of force. The result you get is all about their mass. Give a low-mass baseball that push, and it's going to take off with a huge acceleration. Now use that exact same push on a high-mass bowling ball, and it barely moves. You get a tiny little acceleration. It's so clear. More mass means less acceleration for the same push. So, Newton gave us one last, really profound rule. And this one isn't just about how one object behaves, it's about how any two objects interact with each other.
It's like the universe's fundamental law of balance, this cosmic pushback.
This is Newton's third law. What it really means is that forces always come in pairs. You can't just have one. When you push on something, that something is pushing back on you with a force that is perfectly equal and perfectly opposite. There's no such thing as a solo force in the universe.
Here's a super tangible way to think about it. If you push your hand against a wall, the wall is, at that exact same moment, pushing back on your hand. The pressure you feel on your palm, that is the wall's reaction force. It has to be there. Now here's where it gets a little mind-bending. This law is universal. So while the Earth is pulling you down with the force of gravity, you are at the same time pulling the Earth up with an identical force. Now the only reason you don't see the Earth come flying up to meet you is because its mass is so ridiculously huge that if you go back to F equals ma, your tiny little pull creates an acceleration so small it's basically zero. But the force, it's there. So there we have it. 3 laws: the law of inertia, F equals ma, and the law of action-reaction. And understanding these isn't just some abstract physics exercise. They are literally the tools we've used to build our entire modern world.
These 3 little rules are basically the instruction manual for how the universe works, at least at our scale. They explain why a car needs an engine. They tell us how to design a skyscraper that won't fall down. And they let us calculate, with incredible precision, how to launch a satellite and put it in orbit around Mars. It's all one elegant framework.
But here's the thing. These laws have their limits. They start to break down when things get really extreme, at speeds that are close to the speed of light, or in the bizarre, tiny world of subatomic particles. So the final thought is this. If Newton's laws built our world, what kind of physics governs those other, much stranger worlds out there?